NTU World of Wisdom. Welcome to High Impact Thesis. In this podcast, we speak with researchers from various scientific fields to talk about the motivation, goal, and potential impact of their research. We also want to give you a sense of how a Ph.D. is carried out with an emphasis on the PH, the philosophical aspects involved in pursuing a Ph.D.
So, Sarthak, welcome. It's good to have you with us today.
Thank you. It's a pleasure being here.
So, we'll be talking a bit about your research today, and maybe we could open up our conversation by asking you to give us some general background about your research area in broad terms, and then maybe we could get into more details about your work personally at some point later as we go on.
Sure. Yeah. So, I'm Sarthak. I'm a part-time PhD student in NTU, in the School of EEE. Although my work has nothing to do with electrical or electronic, actually it has something to do with it, because my PhD is mostly in a field called space physics, or you could also call it planetary science. I'm investigating gravity waves in planetary atmospheres. Just a disclaimer, these are not gravitational waves that you see in the cutting edge physics.
I wanted to ask you about that,
Yeah, it's not. So just a disclaimer right there. So gravity waves are waves in the atmospheres. They happen in all kinds of fluids. Think of them as ripples on a pond. Mm-hmm. And the same thing happens in the air on all the planets. So the reason why it's important to talk about these waves is because they play a key role in energy and momentum transport in any planetary regime. So what these waves would do is they would get generated in the lower part of the atmosphere of any planet through events like anything which has energy dump. So convection, seismic events, earthquakes and stuff. Could be any of those, or heating processes. And these waves would be generated and then they will propagate. As they propagate upwards, their amplitudes increase because the density is lower as you go up. And at some point, they become unstable and break. So when these waves are breaking, that's when they're depositing all the momentum and energy that they were carrying from the lower atmosphere. So think of it as an energetics coupling process.
So it's primarily between two different mediums? Would that be correct to say that?
If you treat the atmosphere as different layers, you could say so. But think of it as waves traveling in a continuum. It's a fluid mechanic phenomenon.
All right.
Yeah.
So now maybe we could go into more details about what you personally do here at NTU, what you're trying to achieve with your research.
Sure. So as I mentioned, I'm a part-time student over here in NTU. Full-time, I have a job with this company called Analytical Graphics, AGI. We are now acquired by ANSYS, so you could say I work for ANSYS. We are a modeling and simulation company. We perform modeling and simulation and provide software for such for aerospace and defense domain. My work mostly has to do with astrodynamics, which is orbit prediction, modeling of spacecraft maneuvers, orbital dynamics, as well as UAVs, aircraft, and communications, radar, like strategic systems. So that's what I do. So that's my day job. And this PhD that I have in science is a part-time PhD to balance out my engineer side.
So what did you do before you get into this gravitational wave research? What's your undergrad maybe, or what's your background, educational background?
Yeah, so I was an undergrad from NTU itself, NTU Aerospace Engineering class of 2014. So that's where I graduated. I worked at Rolls-Royce at NTU, Cop Lab for 2 years. So over there I was working on jet engine manufacturing processes. So that was manufacturing material science work. Then I moved to a startup doing UAV design, which crashed and burned spectacularly. After which I came to the Satellite Research Center in NTU, which happens to be in EEE. And that's where I worked for 2.5 years as a research engineer. So that's where I was developing attitude control systems, which is orbital dynamic stuff for spacecraft, as well as performing systems engineering and mission design for spacecraft missions. That's what I did. And then while I was there, I started a PhD part-time. And at some point, I moved out into my current job. Yeah.
So you're already 3 years into your PhD now, or
Oh yeah, this is my 3rd year running. Yeah.
Okay, so maybe if you could speak to the motivation behind, why did you choose this area and not other areas to do your research?
That's a great question. I get asked that a lot. And even I ask that myself, why am I doing this?
Yeah.
So, Many reasons. Well, first is, so I've always been very interested in physics and math, right? So that's my thing. I didn't get to pursue physics as a full-time thing because I chose engineering that route, right? And I got into engineering, yes, but I also wanted to have some science experience, which I didn't have. So I thought I should balance out this engineering with my science PhD. That would be nice. Another reason for doing that would be because the field that I'm in space science or spacecraft engineering, there's really a lack of people who understand the science aspect as well as the engineering. Mm-hmm. So the reason why you do space exploration is because you want to find out a lot of things about the universe and the way it works. Mm-hmm. And that is usually driven by scientific hypothesis and done by scientists. But to verify those hypotheses, those theories, you need instrumentation, which will go out, measure things, or observe signals, and that is often done by engineers.
All right.
And both of these people, they're operating simultaneously in a highly constrained environment. You have scientists trying to work on hypothesis with lack of observational data, and engineers are working on cutting edge missions, but they are either underpowered, under-resourced, or just not in the position to be able to observe what needs to be observed. So, and these two different camps of engineers and scientists don't really understand each other's constraints very well. So having a PI, a principal investigator, leading a mission who has both engineering and science experience is extremely valuable.
Mm. So it's more of like an interdisciplinary work.
So basically, yeah. Mm. Agencies like NASA, ESA, they highly favor such individuals to lead their missions. So looking at that from the long-term perspective, I thought it would also be nice for me to get this. And all in all, it gives you a very well-rounded, representation of the whole field that you're working on.
Mm-hmm. Okay, I'm curious to know, like, on a day-to-day basis, how does your research activity looks like? Is it modeling and simulation, or is it like involve some experimental work, or how does it look like?
So it's a blend of everything, as you would expect. So there's a lot of modeling and simulation because we can't really do a lot of experiments, but we do, of course, have a lot of observational data. So in my work, I harness a lot of data that has been collected by others, and I just leech on it. So this data can be either for Earth, for example, collected by GPS receivers. For other planets, it's collected by different planetary spacecraft, like specifically Mars and Venus, for example. So I leverage on the data that has been provided by other missions. I don't do any experiments by myself, or we don't develop any instrumentation by ourselves for that. And I develop my own codes to perform the modeling and simulation of the processes that I'm studying.
Mm-hmm. But when you say observational data, like data of what exactly?
Right. Good question. So as I mentioned, we are looking at the waves, and I think this is something I should have spoken before about. Yeah. The immediate implications of why would anybody want to even study these waves. So let me talk about some quick, very close to home examples for us. Yes. So these waves go up. I talked about some waves which get generated by some energy processes, and they go up. As they go up, their amplitudes start increasing until they become unsustainable and they start breaking, overturning, and that's where they deposit the energy momentum. Right. Now on Earth, for example, this usually happens around the ionospheric layer. Right. So when that happens, ionosphere also ebbs and flows. Right. So you have regions of compression and rarefaction. So you have plasma density and electron density increasing and decreasing in different zones. And now, as you know, RF propagation through any medium is dependent on electron density. So one example would be the GPS signals. So if you are looking at the GPS receivers and there's some anomaly in the local ionosphere, and I think Grace is the person to talk about that. So when that ray coming from the GPS satellite to your receiver in your smartphone, for example, is going through that ebb and depleting region of the ionosphere, it's going to have refraction. And it's going to have refraction depending on how much the density has been modulated by these waves. And that's going to cause errors. Phase lags is going to cause errors in your navigation system. Mm-hmm. So this is very important as you move toward autonomous vehicles. So that's one reason why you want to study these kind of waves and predict them if possible. Which also gives you a very nice way of detecting these waves. So one of my first papers, which is just going to be published soon, is simply about detecting these waves caused by an earthquake in this region, Southeast Asian region, through a dense array of GPS networks that has been placed by the Earth Observatory of Singapore. That's one. These waves, these gravity waves, have a lot of effects on overall climate of a planet. Climatology, it affects that, but we will not go in there because we're talking about engineering. These days, you guys are aware of OneWeb and SpaceX constellations. Okay?
What's that?
These are very low Earth orbit constellations to provide internet. And all these satellites are going to be flying very low. So low that the atmospheric drag actually becomes significant. And guess what? These waves modulate the atmospheric density as well, which can be significant for these satellites in terms of how fast is the satellite going to decay or how is its orbit going to drop. So, yeah.
Does that interfere with the transmission of these satellites, like the waves and you just described?
Well, radio waves definitely, but that's not really a concern because these signals are going to be very high C/N, like carrier to noise ratio. But it's definitely going to be a consideration for orbital dynamics for such low flying satellites because they need to keep providing orbital burns to ensure that they stay in the required orbit. And there's going to be so many of them, keeping track of them is going to be a messy affair anyway.
You just mentioned something about autonomous vehicles. What do you exactly like? Why are autonomous vehicles consideration here in this?
Well, that's just an example. And
Like
the reason why I would say that.
Autonomous cars, you mean, or autonomous?
Yes.
Okay.
Even UAVs for that matter. Anything that relies on precise guidance.
Okay.
And that guidance is being provided by a GPS receiver is a likely candidate.
Okay, so this is really about your research in particular. I want to also focus a little bit on the general outlook of this field as well as the tools you use in general that other people, perhaps researchers, could find useful as well. So I'm interested in your background as a space engineer in particular, since you also have been involved, for example, in NTU missions, space missions, for example. I would like to hear a bit about what is your feel for what is happening in the space industry currently, and what's the future looking like for us as mankind in general, in a more general sense, since it's an industry that perhaps, in my understanding, has been traditionally been about a few players, and now it seems to be a lot more people coming in. What is your feeling about that?
Right. I mean, you're absolutely right about what you just said, and maybe this gets thrown about a lot, but it's actually true that this probably is the best time to venture into space. Because like right now is the time when we are actually reaping the benefits of the miniaturization that we've had in technology, the maturization and the low cost of processors, embedded systems in general that we have had. That a lot of people, a lot of institutes, even universities and high schools for that matter, can actually afford to make systems that can go up in space, right? At the same time, you have multiple launch companies which are providing you competitive pricing for launch. So you have a lot of avenues to, like building hardware is one thing, but actually launching it is equally important, right? And you actually have those competitive prices to be able to put your stuff up in space. So definitely a very exciting time to get in there, right? What I can see, so this phenomenon, you can call it the democratization of space, right? So we all get access to space. Very exciting time to be in. What was the question again?
And I'm interested in, so for example, the fact that right now more and more people can be involved in space obviously means that certain things that perhaps would have taken much longer to do can be done faster, as in going to Mars, for example, right? And I'm wondering what would be the impact on our society of such kinds of innovations, not just from a technical point of view, but from a social point of view. What would that mean?
Good question, Ab. So here's the thing. So there are two ways of looking at it. One is how do progress in space sciences, spill over to other fields. Mm-hmm. And I think we have talked about that. A lot of people have talked about that. But let's just focus on this itself. How just going out in space, and by more people going out in space, how's that going to help us? So one thing for sure is that we are going to understand things a lot better. Right? So besides astrophysics, which is having advances, let's just talk about our Earth system in general. So with all that, Earth's climate is a very complex thing, and we do not fully understand it. There's a lot of uncertainty around a lot of processes that we observe. Right. So just by having a lot of people who are interested in space science and Earth observation in particular, we can have a lot of enhancement in our understanding of how the Earth climate evolves, how human activities have contributed to all that debate is about. That's one. Venturing to other planets. So think of it like this: we are just a happy accident on this Earth. There's no reason why we should be confined to this place, right? It's just like, a species on one island doesn't have to stay on that island. At some point you will be crossing that ocean and going to look for the new island. Whether you go to live on it or not is another matter. So that's our fundamental instinct as explorers. And that is definitely going to happen at some point or the other. Just yesterday, you probably saw the video of the first helicopter on Mars, which happens to be the first.
Oh yeah, I've seen that one. Yeah.
So that's like the Wright brothers moment. That's like slightly over 100 years after the first powered flight took place on Earth.
But I don't know why is it something very significant, like it's on the news and...
It's very significant because this is the first time we have had an airborne flight for a heavier than air vehicle on any other planet.
From a planet.
On any other planet besides, except Earth. We've never had a drone fly on any other planet before.
No, but they land, right? Or is that different?
That's not a powered flight. That's descent. So it's like a parabolic trajectory. You throw something, a stone is going to land. If there's gravity, a stone is going to come down. But are you going to be able to take
launch,
stone
to launch. Okay.
and launch the way you want to, come back?
What's
That's very
the
significant.
gravity of Mars?
It's much less than that of the Earth. Actually, Mars is about half the radius of the Earth. I think gravity is just a few factors lower than Earth.
Is that just the parameter that we change in the equations, or is that a whole different?
It's a whole different thing. You change the parameter, but for everything. So the air is different, for example. So the surface density at surface is about 10,000 times. So that's 4 orders of magnitude lower than what you have on Earth. Now, if you know anything about aerodynamics, so how a rotorcraft helicopter would work is that blades are spinning. You're going to take this air above you, this column of air, and throw it down. And hoping that the momentum that you caused should be enough
pushing you up
to provide enough lift for you, right? That's the basic tenet of rotorcraft. And when the air is thinner, which happens to be for Mars, this momentum is going to be like 4 orders of magnitude smaller, which means you need to spin faster.
I see. So it's because of the atmosphere density?
Yeah.
That's why helicopters cannot go to very high elevations?
Exactly.
Oh, okay.
There's a service ceiling for all the helicopters after which they just...
Because the air get thinner as you go up.
Exactly. And that's an exponential drop.
And how different are the atmospheres between Earth, Mars, and Venus?
Quite. Well... So
both in terms of composition as well as in terms of in whatever other fashion then.
So first let's talk about composition. So on Earth you have nitrogen, which is about 71%. It's a diatomic molecule, right? You have oxygen, which is about another 23%. And then argon and CO2 and traces, water vapor, all that. On both Venus and Mars, the dominant gas is CO2.
Okay.
Right. That's what it is. How Venus and Mars differ very differently is that Venus has very high density. The atmosphere is much, much thicker than Earth, while Mars has a very rare atmosphere. It's very thin.
Mm-hmm.
So you have a hard time flying a helicopter on Mars, but it should be a breeze on Venus. In fact, there are concepts of having boats on 80 kilometers above Venus, because the air at that level, the atmosphere at that level is the same density as you have on Earth, for example. So if you have floating balloons or that kind of craft at about 80 kilometers above Venusian surface, it would feel just like you
could easily sustain them at that elevation.
You could, because the air below is way denser, so that's going to support it. But again, this is all carbon dioxide, and you have a lot of clouds around you, and those clouds are sulfuric acid on Venus. So maybe not that great an idea.
Oh, okay.
On Mars, you have clouds too. You have clouds made of carbon dioxide, CO2, which happen once in a while. Mars is very dusty, but that's not air anymore. Yeah. So mostly in these ways. So they differ in composition, they differ in their densities, and that has to do with the way these planets have evolved.
Okay, and as a researcher yourself, I'm interested in understanding what are some tools that have been helpful for you in general, not just specifically for the work that you do, whether MATLAB or what, but in general, maybe to navigate whether it is the social dynamics of doing a PhD or actual academic work.
I think, and I think this is what you all researchers would agree with, is that just coming into this field, the first thing you need is ability to think critically. Being able to question or being able to formulate a hypothesis and being able to test its validity against different claims, against different observations. That's the first thing. Being able to critically analyze any situation. So that's critical thinking. That's our level 0. You need that, right? Then you come in, you need domain knowledge. You don't just need domain knowledge in your specific field you're studying, but in fact you need decent exposure to different fields in varying degrees depending on what you're working on. You need a lot of familiarity with mathematics and statistics because you will be, these are quantitative sciences we're talking about, so you definitely need that. To work on those mathematical and statistical techniques, there will be some toolkits, some softwares. So take your pick for programming language, statistical software, plotting utilities. So these are basics. I think these are some things everybody needs. And after that comes what is really required for your field. Now, this is just a scientific process, tools to do your science. And then you have to communicate that. Yeah. So you need to start talking about your research. You need to start writing your research so that gets published. Yeah. So writing skills, talking skills, making a poster, writing a paper, and all these are their own, like beasts in their own regard, because writing a paper is not simply you wrote a report and you send it in. There's a whole process of, first there's a way of doing it, right? When your papers become complex, tracking citations, all that, you need the tools for that. You have EndNote, Mendeley, all those things, which we all learn only once we are in, I think, second or third year of our PhDs. You need those tools. And the process of writing a paper, writing to the editor, getting the reviews, how do you respond to the reviews, how do you structure your comments, that's an art in itself. Yeah. So all these things one has to pick up. Presentation and conference, how do you do it? How do you network with your fellow community? How do you sell your research? Yeah, I guess that's what's needed.
Okay, cool.
And it's a lot.
And would you, this is a generic question, but there are things that you wish you had known before entering this PhD area that you wish someone had told you about?
Of course, I mean, this is a question that always has a resounding yes as an answer whenever you ask this to yourself, right? Yeah. And not just to PhD, whenever you ask, like, oh yeah, I wish I had known this before. Because in the hindsight, whatever you look at, feels like shouldn't have taken that long or shouldn't have been that complicated. But whenever you do this kind of retroactive thinking, you're always missing out the fact that the past you was a different you altogether. You simply didn't have those skills, that expertise, those capabilities. So it probably is not very valid to ask these questions. But I would say if I had known something better, would be this whole process. Probably this whole process of structuring, formulating science questions, formulating a research plan, publishing process in general. If I had known about these things, and these are soft skills, these are not something you go to a school and learn. These are some things you only learn by doing. Yeah. If I had this experience, I feel that my progress would have been significantly faster.
Okay, so we are interested in you beyond the research and the scientist that you are. We would like to know a little bit about what you do outside of work and outside of research. What pursuits do you have?
In terms of hobbies, you mean?
Could be, yeah.
You can call them hobbies, yes. Could be any other thing.
Sure. So when I'm not working or not working on my PhD, of course, I do have some hobbies. So I'm into powerlifting. That's a sport I have. I think if you're doing a lot of mental work, you need a lot of physical work as well to balance it out.
Yeah.
Okay.
It's just my feeling. So I've been active in powerlifting. I'm also interested a bit in music, specifically rock, metal, heavy metal. Oh. I play drums. Play the drums.
Interesting.
I do these things on my free time. And if I still have free time, I would like to play some video games and sleep.
Do you play the space video game? The space game, what do they call it? Kerbal Space Program?
I do have it. I have fiddled around with it, but not much.
Okay.
I haven't played with it as much as I have played in STK.
Huh?
STK.
Then you can play games on STK?
Well, it feels like a video game.
What's SDK?
SDK is a software which my company makes. Shameless plug. But no, SDK is the industry standard software for astrodynamic simulation. It feels like a animation video game and all that, right?
Mm-hmm. Does SDK, I think it stands for, sometimes I found like software development kit or something.
Oh, that's SDK. This is STK, Systems Tool.
Oh, T, not D. Okay.
Yeah, Systems Toolkit.
All right.
Yeah.
Very useful things.
Yeah.
Any other interesting things about space that you'd like to share with our audience today?
Keep space in your thoughts. People often don't think about it. We are often so fixated upon our problems, our issues, that we usually trapped in our own, tiny little world. But it's helpful to put things in perspective once in a while, zoom out a bit and see where you actually stand. And once you are observing things or contemplating things at the level of the cosmos, you realize how insignificant you yourself are, and then your insignificant problems. So that's going to give you a lot of peace of mind, and that's probably one of the most satisfying things you can ever experience, in my opinion.
Yeah, it's very nice actually, because I think of the fact that right now we're one planet. I mean, we're on one planet out of potentially, people are estimating 400 billion galaxies, and every one of those has got about a couple of billion stars and so on, right? So we are like really exploring a tiny sleeve of the universe. So to me, space is very exciting because
it's a staggering. So again, there are two ways of thinking about it. One is, oh, look, here we are on this planet. How many more planets could be there? And you just gave me the number 400 billion.
That's galaxies, but yes.
So that's just one way of looking at the staggering scale. There's another way of looking at it. Even if, let's say, we are the only ones, like our planet is the only one with life on it, just think about what a sheer accident it must have been to make that happen out of all those possible worlds. Forget about all the possible extraterrestrial life. Just think about your own existence. What brought it? Sun, our star, is just a regular, ordinary, is an average Joe in the star world, right? Our planet is just a regular planet. Nothing special, remarkable about it. It just happens to be at the right distance, not a bit too close, not a bit too far. Just a happy coincidence of a lot of things, and here we are after millions and millions of years of evolution. So just think about how remarkable and how rare that process is. So, and think about you yourself, like you are a product of this incredibly rare event, which has like almost zero chances of happening in the universe. So you got to do something with that, right?
You got to be excited about it.
You got to be excited about your existence, definitely, and you got to make your existence worth. Like do justice to that rare event that created you, and make your existence worthwhile.
Okay.
All right.
I had a question. So the degree that you'll be getting is Doctor of Philosophy, right? Like this 4 years of Ph.D. and the degree conferred would be a Doctor of Philosophy. So how do you think in terms of the philosophy of your thinking, things have changed for you? So how did you used to think before and how do you think now? What is maybe a philosophical difference in how you approach problems or life in general, or how do you think different?
Good question. Something that does make me think about, like, besides doing this fun little project that a PhD is, and getting that title, what exactly does it mean, and how does it change all of us as people?
Yes.
So again, first, this is probably a very straightforward thing to understand, but I can't insist how important it is to realize, is the fact that by going through this whole process of a PhD, you actually become a rigorous practitioner of philosophy in general. So philosophy is the study of knowledge, right? And how it works is argumentation. Put forward a hypothesis, arguments for, against, fight it out, and the argument that stands wins. And your PhD, my PhD, is no different. I came with some nuances, and I find evidences for and against, and you pit them against, you do your work, the grunt work, and then in the end come up with a conclusion. And you take that as the truth, and you put it forward to people of similar caliber, if not better, and let them examine it, and it's all out there. So this is what I think has translated into my life as well. So I feel that I've become a much more methodical thinker. I've been more open to criticism than I used to be before. Like instead of just going with my instinct all the time, I'm much more comfortable now with, the uncertainty of what could be the truth, and just going with my best guess, and having others, my friends and people close to me, examine my thinking, pick it apart and say, hey, yeah, maybe, this could have been different, this could have been better, all that. So I think all in all, the first thing it has made me into is a better thinker. After this, I don't know what else it has taken away a lot of my brain cells. Yeah.
Thanks.
That's quite interesting.
Does that answer anything?
leave it to
Yeah,
the
I think it's
audience
an
to-
interesting to be.
Okay, if Chris says it's interesting.
It's because it really is important to think about it from a more general, not really specifically what have you done, but what has it done to you, the process of going
Like,
through
I'm
this.
never gonna this gravity is immaterial to me, like after
Right.
the PhD is done, right?
So it's
But the process of doing it,
right. I think that's hopefully that's something that can be applied beyond your PhD, and that's why it's worth perhaps dedicating 4 years to do it. I heard it somewhere said that science is a way of thinking, in a sense that it's a way where you know that I making decisions based on this particular data. If the data changes, then I have to update the way that I view the world.
Yeah.
Right? And I think that can be applied in a lot of areas. So I think to me that's an interesting thought that you brought up, that you're changing how you think about the world because
Certainly.
you realize there is uncertainty in everything that you're
Another important point I may emphasize is that science is also about being uncomfortable with the fact that you are not sure of anything. We are living. So we want assurance. We want to be very sure of things. We want to know if this is correct or not, and we want it now. Science tells us to be patient. Science, this whole process of doing the science actually inculcates that in you, that you are open to both, and you will lean with the side which has more weight of observations of credibility. And you know that also it can change in a swing. For example, look at math, right? Math works. Mathematics works. It works on logic, right? And how do we know? It's because we have a formal construct which, through methods of proofs, has been consistent, and it has been consistently giving us the same results as what we would expect in nature. Right.
Yeah.
If one day far along the line it were to fail, we will have to question this whole framework of logic and mathematics that we built. Right. And for a scientist, this is nothing. Like, it's just another day at work. For some of us, it can be a huge deal. Like, oh wow, the whole world is turned upside down. But this is just another day at job. Maths doesn't work today. Doesn't matter. Let's find out what works, and then we'll make those corrections and we'll move on. So, being open to all the possibilities, not siding with just one thing and sticking by it, just keeping your mind very open, and being open to the evidence that's coming in, siding with that. I think that's a very important thing.
Okay.
All right.
Okay. So, Sarthak, thank you so much for your time. We appreciate you sharing about your research, what you do, as well as why you do what you do, but also the general tips you've shared with our listeners about the process of doing a PhD, as well as how it has changed you as a researcher. So we really appreciate your time and sharing your wisdom on this. Thank you very much.
Thank you.
Thanks a lot, guys. It was a pleasure. Thank you.
Thanks.
Thank you, Sarthak.